Today, Irene Malmierca will present her study, Dansgaard Oeschger events in common models, review and baseline Marine Isotope Stage 3. So it's a long title, whenever you're ready.
Yeah, sorry about that. It's a very
No.
So let's see. Am I sharing now the slides? Can you see the slides? Good. Okay. Let me see if I could get the pointer. So yeah, I'm gonna talk about this paper that we have recently published in Climate of the Past with the very long title, Dansgaard-Oeschger events in climate models. And we are trying to put together this new PMEP mystery DO protocol. And also I will talk a little bit about some preliminary results. So I'm also at the moment looking at the impact of CO2 on DO type oscillations in different climate models. So I will talk about that a little bit as well. So in terms of the protocol and the paper, you can see that there are many people involved. So yeah, I mean, it's kind of a big international effort, and we call us the PMEP DO community. So for the last few years, I have been trying to, well, first of all, I have an introduction of DO events. So what is a DO event? So here you have the North Creep temperature reconstruction for the Marine Isotope Stage 3 between 28 to 58 Ka. And you can see that a number of DO events happen during the Marine Isotope Stage 3. So during a DO event, Greenland transitions from a cold stadial to a warm interstadial, and we have the abrupt warming event, and temperatures could increase by 10-15 degrees Celsius during this abrupt warming event, and it happens like in a decade. And then we have the gradual cooling phase, which takes longer time, and then, well, this yeah, we can see DO events also in the Antarctic temperature stack records from Antarctic ice core records as well. The DO events are visible. So yeah, during the last few years, I have been really focused on trying to kind of answer this question, or it will be like the big motivation of the research, which is trying to check if our current climate models are too stable to simulate DO events, past tipping events. And this is a really important research question that needs to be answered because, yeah, I mean, if our current climate models are too stable to simulate these past tipping events, past DO events, simulations of the coming century might give us a false sense of security. And so during the presentation, I will try to cover these 3 points. So the first one, what fraction of models can and cannot simulate DO events, and how sensitive are they to forcing? The second point, what are the mechanisms behind these DO events, and if they are similar between different models? And the third point is, what are the implications for climate projections? So in terms of the first point, we have around 39 CMEP6 models, and you can have a list there. It's not a complete list, but the key point here is that only a few of these CMEP6 models have been used for some kind of paleoclimate simulation. So here in this other list, you can see the few models that have been used to run some kind of paleoclimate simulation. And of all of these, only a few of them have been run an LGM or a mystery simulation. Only one model has run a mystery simulation. So this is one issue for us, for modelers, for paleoclimate modelers. And then if you look at the run length of the simulations, basically, if we want to check the capability of the models to reproduce these past DO events, we need to run long simulations for at least 2,000 model years, I would say, with a decent spin up of 1,000 years. And you can see that some of the simulations have not been run long enough to be sure if the model has the capability to oscillate or not. So yeah, in terms of how many models can reproduce this DO type behavior, these DO type events. So in this other table, I have in the first section all the PMEP4 LGM simulations that have been run with different models. And out of all of these, only one model, the CCSM4, is able to replicate these DO-type events. And here you have some of the CCSM4 simulations with the AMOC time series, and you can see, that the model spontaneously reproduces these DO-type oscillations. Then in the second section over here, I have models that have been used to run some kind of MIS-3 mid-glacial condition simulation. And in this section, we have HAT-CN3. So here you have one of the HAT-CN3 simulations that oscillate, which has been run under 30 Ka boundary conditions. And you can see that the model is able to spontaneously reproduce this millennium scale climate oscillation. And then we have the Cosmos model, MIROC4M, and again CCSM4, because it's kind of a lower resolution version than this simulation over here. And then we have a third section where some models oscillate when they use some kind of mixed forcing simulation. For example, the case of MPISM, they have run a simulation using LGN, last glacial maximum boundary conditions, in combination with a pre-industrial ice sheet configuration. And here you have one of the MPISM simulations, so you can see again that the model spontaneously replicates this DO-type behavior. And there is one more model, and so I heard this talk in EGU, and apparently there is one more model, the CESM, which also oscillate at 38 Ka conditions. So those are the models that oscillate and reproduce DO-type behavior. So yeah, very few CMEP models show this DO-like behavior. Some models which are set up with more MIS-3-like conditions do exhibit this DO-type behavior, but others do not. So yeah, however, very few CMEP5, CMEP6 models have run a MIS-3 simulation. And some of the issues, for modelers, not all modeling groups run paleo simulations with their models. We need to run really long simulations, and this is very expensive, computationally speaking. And there is a lack of a common framework, and this is why, we are trying to put together this new MIS-3 baseline experiment, MIS-3 PMEP, MIS-3 DO protocol. It could really advance, our understanding of the mechanisms behind DO events if we could have these common guidelines out there. So how sensitive are models to forcing? So we have, so this is the HAT-CN3 simulation run at 30 Ka that show these spontaneous DO-type oscillations. And we find that the periodicity between the DO-type oscillations is 1,500 years. And during stadial phases, we have weak AMOC and widespread sea ice coverage across subpolar Jaeger and Gene seas, which is kind of expected compared to interstadial phases. So we have run a range of sensitive simulations with HAT-CN3. The first set of simulations looks at the sensitivity to CO2. So we took the 30 Ka control run, and we kept all the boundary conditions as for the 30 Ka control run. And in this set of simulations, we only modified CO2 values. So we give values between 100 to 600. And so the idea is that here you have all the AMOC time series of each one of the sensitive simulations. And HAT-CN3 oscillates in a very narrow window of CO2 concentrations between 185 to 220 ppm. Then we ran another set of simulations with HAT-CN3 with different orbital parameters. So again, we took the 30 Ka control run, and we kept all the boundary conditions as for the 30 Ka control run. And in this case, we only modified the orbital configurations. So instead of using 30 Ka orbital configuration, we use orbital configurations between 0 Ka to 42 Ka. And yeah, the key message here is that we find that in HAT-CN3, low obliquity helps to basically decrease the high latitude mean annual insolation, and that triggers change in North Atlantic sea ice, and that basically triggers the transition between interstadial and stadial phases. And then we have another set of HAT-CN3 simulations where we look at the sensitivity to Laurentine ice sheet height. So again, we took the 30 Ka control run, and we kept all the boundary conditions as for this 30 Ka control run. And for this particular setup, for this set of simulations, we modified the height of the Laurentine ice sheet. So we scale up and down the height of the Laurentine ice sheet by a percentage. And yeah, we find the key message is really that HAT-CN3 again oscillates in a very narrow window of Laurentine ice sheet height. So it oscillates when we have kind of an intermediate low size. So I have covered my first point, so I will go to my second one. So what are the mechanisms behind DO events, and if this is similar between different models? So yeah, at the moment I'm looking at this atmospheric CO2 impact on DO type oscillations in 3 different climate models. So this is the CCSM4, MPISM, and HAT-CN3. So for the CCSM4, Guido Vettoretti, he ran a set of simulations where he was using last glacial maximum boundary conditions. And the CO2 range that he used was between 170 to 240. And I have highlighted in blue, basically the simulations that oscillate, that reproduce this DO type behavior. So CCSM4 oscillates between 185 to 230 ppm. And here you can see some of the CCSM4 simulations that oscillate. So in blue, I have the model temperature over North Crib ice core side. And then we have a set of MPISM simulations, which, yeah, these are mixed forcing simulations. So they have been run using LGM boundary conditions in combination with a pre-industrial ice sheet configuration. And the CO2 values that they used was between 149 to 353. And MPISM oscillates between 195 to 217 ppm. And yeah, here you have the model temperature over the North Crib ice core side for these 3 MPISM oscillatory simulations. And then we have HAT-CN3. I have already talked about this set of simulations. So they were all run with 30 Ka boundary conditions, CO2 values between 100 and 260, and HAT-CN3 oscillates between 190 to 220. And here you have the plots for the HAT-CN3 oscillatory simulations. And yeah, first of all, the 3 models oscillate in a very similar narrow window of CO2 concentrations. And also it compares remarkably well with MIS3 CO2 values. So the 3 models oscillate between 185 to 220. And this compares remarkably well with MIS3 CO2 values, which range between 187 to 233. And in these other subplots, if we look at, so again, these are the same simulations, the 3 MPISM oscillatory simulations. The second column is for the HAT-CN3 runs, and the third one is for CCSM4. And in orange, I have AMOC time series, again in blue, model temperature over the North Crib ice core side, in red, west divided ice core side, and in cyan, North Atlantic sea ice area. So in the 3 models, as expected, we find that during interstadial phases, we have a strong AMOC, we have increased temperatures over Greenland, decreased North Atlantic sea ice area, increase in North Atlantic salinity. And in the 3 models, we have this anti-phase hemispheric temperature change between Greenland and Antarctica. So the Greenland stadial phases, basically, they happen at the same time as we have this increase in temperatures over Antarctica. So this is true for the 3 models. And now, yeah, I have found that CO2 is bound in an oscillatory DO sweet spot, and I will explain what I mean by this now. So in this subplot in blue, I have the HAT-CN3 runs, black for CCSM4 and red for MPISM. And in the x-axis, I have CO2 values that were used for each one of the sensitive simulations. And the y-axis is just a simple measure of increase in temporal variability. So I have just calculated standard deviation over the AMOC time series. I have done the same, but in this other subplot, I'm using standard deviation calculated over the North Atlantic sea ice area time series of each one of the sensitive simulations. And the key message again is that the three models oscillate in a very similar narrow window of CO2 concentrations. And we have two stable states where models do not oscillate. So we have one stable state with low CO2 values and weak AMOC and extensive North Atlantic sea ice area, and another stable state with high CO2 value, weak AMOC, and reduced North Atlantic sea ice area. And then, in this subplot, basically I'm showing salinity differences between each one of the sensitive simulations and the sample mean. And the sample mean has been calculated considering all the models, all the simulations that oscillate between a model. And in particular, I'm looking at salinity differences during the stadial phase. So the first column is for the 3 MPISM simulations that oscillate. The second column is the HAT-CN3 simulations that oscillate. And then we have the CCSM4 in the last column. And so, you can see, and the first row is the simulations that have been run with lower CO2 value. And the last two rows are for the simulations that have higher CO2 values. So basically, if you look at the plots, when we have higher CO2, we have more red here. And if we have low CO2, we have more blue. So what this means is that in these high CO2 experiments, we have an increased mid-latitude Atlantic salinity build up in the upper ocean during the stadial phase compared to the sample mean. So this helps to reinvigorate the AMOC. And so the system spends less time in the stadial period. And in this other subplot over here, again, the same colors, blue for HAT-CN3, red for MPISM, and black for CCSM4. In the x-axis, I have the CO2 values implemented on each of the sensitive simulations. And in the y-axis, I have the time spent in stadial phase. So you can see that it's true that as we increase CO2 values, it seems that for the 3 models, we get this decrease in the time spent in the stadial phase. So the key message is that in the 3 models, CO2 is acting as this internal climate element, modulating the timing characteristics of the DO-type oscillations. So overall findings, we find that models tend to reproduce this DO-type behavior when they use kind of an intermediate ice sheet configuration, not a full last glacial maximum ice sheet configuration. And that models tend to oscillate more easily when they use medium to low CO2 values and when we have low obliquity values. Another important conclusion is that some models which are set up with more mystery-like conditions do not have this DO-type behavior, but others do. Most modeling groups have not run simulations of long enough duration to be sure which models to capture this DO-like behavior. And so this perhaps can be rectified, and this is why we are proposing a new mystery baseline protocol, PMEP mystery baseline protocol. And we propose to center the mystery baseline experiment at 34 Ka, so we choose the period between 38 to 32 Ka. Why this specific period? Because a number of DO events happen during that specific time window, and also because we find all these boundary conditions under which we think models will tend to oscillate more easily. So we find low obliquity, this intermediate ice sheet configuration, and also we find medium to low CO2 values, which seems to be the 3 key ingredients so to have this DO-type behavior in models. We propose to run this mystery baseline experiment, and in the table you have the specific boundary conditions that we propose for the experiment. In terms of the ice sheets, we propose to use the 35 Ka ice sheet reconstruction, which is published in Go et al. 2021. So here I have a couple of pictures of this ice sheet reconstruction. So the first row is the 35 Ka ice sheet reconstruction, and in the second row, for comparison, you have the I6C, the full last glacial maximum ice sheet configuration. And you can see that, I mean, the Laurentine ice sheet is well reduced, the Cordilleran ice sheet is really well reduced, and also the Eurasian ice sheet is well reduced. So this is the ice sheet morphology that we propose for the baseline experiment. And so this, my last point, what are the implications for climate projections? We are not able to answer this yet. If we could get more modeling groups running this baseline experiment, we could make progress on this, and now it's the time. And with that, I would like to thank you for listening.